Hi, thanks for watching. I'm Jie Chen. I'm going to give you a quick introduction of my work, Correlation Polarimeter-Interferometer in the DIII-D Tokamak. My email is shown here on the left. Please feel free to contact me if you have any question. The motivation of this work. We know that the electromagnetic turbulence is predicted important in Tokamak plasmas, and it's critical to experimentally measure these fluctuations to validate models. On DIII-D, we have developed a radio interferometer polarimeter diagnostics, which have been used to detect program magnetic fluctuations in HMO pedestal that have been reported these results in last year APS. One limitation of this instrument is that the minimum detectable magnetic fluctuation is about 1 Gauss, limited by the noise floor. Recently, a new correlation polarimetry has been demonstrated capable to reduce noise flow by more than 1 order of magnitude. So it's natural that we want to test this out on DIII-D. But it's worth to mention that this correlation polarimetry has not yet been demonstrated compatible with simultaneous interferometry measurement. So that's what we are going to do on DIII-D. So this is what I'm going to show you for my talk. Firstly, we propose a correlation polarimetry interferometry technique to achieve simultaneous polarimetry interferometry measurements with reduced noise flow. We test and verify this technique on the bench, and we also demonstrated the measurement in a DIII-D HMO discharges. So firstly, let's briefly review the fundamental principles of the two-way polarimetry. This kind of polarimetry uses left-hand and right-hand circularly polarized waves to measure the Faraday rotation. And the Faraday rotation is measured usually with high phase resolution and temporal resolution, so that the instrument can also simultaneously measure the fluctuation of Faraday effect, which provides the information of magnetic fluctuation. Based on the two-way polarimetry, we can add another way, which is the local oscillator, as shown here by the green line, so that we can simultaneously measure the Faraday rotation and log integrated density with high phase and temporal resolution. The two-way polarimetry is also the base of the correlation polarimetry. As you can see here, that to do the correlation polarimetry measurement, what you need to do is to introduce a actual detector at each channel, so that at each channel you have two independent detectors to provide two signals for the correlation. The correlation will allow you to reduce non-correlated noise so that the noise flow can be reduced. So now it should be apparent that if you want to do simultaneous polarimetry and interferometry measurement using the correlation technique, what we need to do is to combine this three-wave technique and two detectors at each channel, as I'm showing you here in this slide. So a little detail here is that the local oscillator is only directed to one of the detector, which I labeled three-way detector here in my slides. And the local oscillator is not seen by the two-wave detector, which is the other detector. So this is to avoid the contamination of the interferometry measurement to the correlation polarimetry measurement. In the correlation polarimetry measurement and interferometry measurement, the polarimetry part is achieved by correlating the IF frequency at the two detectors I'm showing here. So in the figure shows you the IF spectrum of the two-wave detector and three-wave detector. So for the correlation polarimetry, what we need to do is correlating the intermediate frequency at the middle, which is 8.6 megahertz, and on the two-wave and three-way detector. For the correlation interferometry part, what we need to do is correlating the 5.7 and 14.3 megahertz signals at a three-wave detector. It should be noted that the 4.7 and 14.3 megahertz signal designed to be at the three-way detector only to avoid contamination. So here we see some finite signal on the two-way detector, and this is likely due to leakage from non-ideal polarizer. So this is the data on the bench, and based on the bench test, so this is the result we got. The figure shows you the power spectral density spectrum for both the polarimetry and the interferometry measurement. And some the data is the calculation is done by using 2 seconds of data, and the even number is 4,000, and data point is AFT is about 1,000. What we can see here is the correlation polarimetry and interferometry noise floor, which is the green curve more than 1 order of magnitude lower than the standard polarimetry and interferometry measurement, which is the red and blue curves. The noise reduction in correlation measurement strongly depends on the event number n. So here we show the average noise flow calculated using different event number n as the x-axis. We can see that as the n increase, noise flow of both correlation polarimetry and interferometry measurement strongly decrease. This is reasonable because more events provide better decorrelation of random noise and therefore lower the noise flow. The noise flow of standard polarimetry and interferometry, on the other hand, has no dependence on n, which is shown by the red and blue curves. For data with given lengths, smaller NFFT allows larger sample number n and therefore lower noise. So here, data length equals NFFT times n. Therefore, when you reduce NFFT, you can have larger n and therefore lower phase noise. So I'm showing you here on the figure calculated noise flow at different n and NFFT. What you can see here is when you reduce the NFFT, then you can use larger n for the same data set and access lower noise flow. It should be noted that for given n, changing NFFT does not affect noise reduction. And we cannot arbitrarily reduce NFFT because NFFT also determines the spectral resolution. Ideally, there's a optimized NFFT and n. So here I'm showing diagnostics that we implemented on the DIII-D Tokamak, and I'm not going to talk about details. Please feel free to contact me if you have any question. So here I'm showing the plasma result. Left-hand figure is the polarimetry, and right-hand figure is interferometry. Solid lines from a plasma plateau using 0.5 second data, and the dashed line is the noise flow without plasma. For the standard measurement, you can see that there's a broadband fluctuation exists up to 500 kilohertz, but beyond 500 kilohertz, it's really hard to tell whether there's any plasma fluctuation or not, because the solid line is very close to the noise flow, which is the dashed line, as shown here by the red and the blue curves. On the other hand, if you look at the correlation measurement, you can clearly see that beyond 500 kilohertz, there's plasma, still broadband plasma fluctuations exist up to around 700 or 800 kilohertz. So this demonstrates the advantage of the correlation measurement compared to the standard measurement. And the same argument is true also for this interferometry measurement shown on the right-hand side. So that concludes my presentation. So we have this polarimetry interferometry technique proposed and demonstrated. And we have also been able to apply it successfully in the H-mode discharge and reduce my amplitude fluctuation up to 750 kilohertz. This new capability is now available to support this DIII-D experiment. Thanks for your attention.